All right, so I'm doing this at 12:30 a.m. on Friday because I promised schoolgirl that I would get this to her. I'm a little bit late. I said it would be about 10 to 15 minutes, and then I forgot I had to check in the girl. So, sorry, schoolgirl, you won't be able to view this until Saturday, sometime Saturday. So, we are talking about buffers, and let me just sort of give some background on the concept of buffers. Next year, when you're taking biology, perhaps with this guy, we're going to be talking about living systems that need to maintain homeostasis. And the term homeostasis means that the internal environment of the cell or the organism stays constant despite the fact that the external environment is changing, is in flux. So, being able to maintain homeostasis with respect to pH is incredibly important. In the human body, the pH of your blood has to be somewhere between 7.35 and 7.45. And if it strays outside of that range, which is a pretty narrow range, as you can see, it can actually be deadly. So, being able to maintain a strict pH is going to be vital for an organism like yourself. So, how do you do this? Well, it turns out that, in fact, no surprise here, we control the pH by using buffers. And what buffers are is a mixture of materials, mixture of ions and molecules that can release or they can absorb protons or hydronium ions. So, and sort of the flip side of this too is that they can also absorb hydroxide ions. Okay, so they essentially what the buffers are going to do, what this mixture is going to do, is to absorb any excess protons or hydronium or hydroxide ions so that you can maintain the pH within a specific level. So if buffer mixtures or buffer solutions are good at being hydronium and hydroxide sponges, we need to figure out exactly what it is that these things consist of so that they can do this. And typically, a buffer is going to contain a weak acid and its conjugate base. A weak acid and its conjugate base. So let's take a look at some of these um, potential pairings that could go into making up a buffer. So if I have a weak acid such as acetic acid, which is C2H3O2, also known as vinegar, its conjugate base, as you probably can predict when it loses its proton to form hydronium, will be C2H3O2 minus, or the acetate ion. And then we can have something like ammonium, and its conjugate base is when it loses a hydrogen becomes NH3, no charge on that. And then lastly, a very important biological buffer pair, which is carbonic acid or H2CO3 and the bicarbonate ion. This is what you have in your bodies to control the pH of your blood. Interestingly, well, yeah, I'll tell you this, although frankly, it's going to probably get lost in your understanding of buffers. In the blood, there's a 1 to 20 ratio of the carbonic acid to the bicarbonate ion. And you'll probably find out about that next year, particularly if you have me as your teacher. So again, the key element to this whole thing is we need to have a mixture that is going to be able to regulate the amount of hydronium or hydroxide. So let's see how this works. Now, I will tell you I'm going to be creating some diagrams here that will be pretty involved, and you'll have to hit pause and try to catch up, but I'm going to be motoring ahead on this. So the first thing I'm going to do is draw a beaker of water. Now into this water I'm going to add a couple of things. So I'm going to show this with these arrows. And the first thing I'm going to add is sodium acetate. Okay, and sodium acetate starts off as a solid. I think it's solid white powder, but when we put it into water, it's going to dissociate and it's going to break up into sodium ions and acetate ions once it goes into the water. Now, the sodium ions aren't important to us, but it's very important that we have acetate ions form when it goes into the water. The other thing we're going to be putting in is acetic acid. So this would be an aqueous solution of acetic acid that I dump into this water. And what's vital for you to understand here is that the acetic acid is a very weak acid, or I shouldn't say very, I should just say it is a weak acid. So in that it's a weak acid, it mostly likes to stay as HC2H3O2. It doesn't really like to dissociate to form the hydronium ions and the acetate ions, and that's a very important thing. So I want you to, in parentheses here, write weak acid and then say so stays as HC2H3O2. Now this is very important because don't forget we're trying to limit the number of protons that end up going into a solution. We don't want to introduce a lot of protons because the whole point of a buffer is to absorb excess protons or hydronium ions. So the last thing we want is to put in an acid that's strong, meaning that it dissociates readily and produces a lot of hydronium. In this case, acetate doesn't like to dissociate, so it mostly stays as the HC2H3O2. Now, that doesn't mean that it completely stays together. You're going to have some ionization. So let's just say for just to keep this whole thing consistent, since you are going to lose a few hydronium here and there, the pH is going to be acidic. So it'll be probably, let's just say 4.74. I kind of just made up that pH. It's going to be slightly acidic, or I guess that's medium acidic. So as a result of putting these two things into the water, we're going to have a bunch of acetate ions as well as a bunch of acetic acid. I'm going to show that in this next picture. So you can see here I have a beaker and it now has a whole bunch of the acetic acid hanging out here. It's not dissociated, it's hanging out together. And then we also have the acetate ion, the blue stuff cruising around here. And remember now, the whole point of this is that if we were to add hydronium or hydroxide, it shouldn't change too much. So how does this work? Imagine for a moment I add in a bunch of acid or put in a whole bunch of hydronium ions. So those hydronium ions are actually going to bind to the acetate ion to form water and acetic acid, like this. Take my H3O plus, which would be an ion in solution. I add in I connect it to one of the acetate ions that are hanging out in the solution. And that's going to form water plus acetic acid. Now, what's really important here is to not forget that acetic acid, which is the dude right here, is a weak acid. And what that means is that this reaction heavily lies to the right side. It really wants to go over towards this direction because the acetic acid likes to form itself. It doesn't like to ionize. It likes to form the HC2H3O2. So if I put in a whole bunch of these protons here, or these hydronium ions, most of them are just going to simply readily combine with the acetate ion to form the acetic acid, and it'll stay as acetic acid. In a sense, it's going to pull all those hydronium ions out of solution. So in a sense, all the hydronium is sucked up by the acetate because this reaction lies to the right. And again, what I mean by that is that it really wants to form the water and the acetic acid. Okay, so that's the easy thing. That's where it makes sense in terms of if you have hydronium that comes in there and needs to be picked up by the buffer. Does that without a problem and maintains the pH of 4.74. So what happens instead of us putting in the hydronium, what if we put in a base, so the hydroxide. How does this help? Well, the same thing is going to happen essentially. We're going to have another one of these reactions go on. In this case, though, I want to remove or suck up, sponge up all these hydroxides. So they go into solution and they combine with the acetic acid that we've put in there. And they form water plus the acetate ion. Oh, that also is an AQ. I just can't fit it in there because I ran out of room. Maybe I can blow it up and put it in there. Very small. Okay, and in this it's slightly more complicated, but it's not that big of a difference here. Don't forget that OH is actually a strong base, because if we define bases through the Bronsted-Lowry definition of bases as something that readily accepts a proton, well, indeed, OH minus is going to readily accept a proton. So it's going to yank that proton that is hanging out here on this acetic acid. Now, despite the fact that acetic acid does not like to dissociate, frankly, it has no choice, because the OH minus, or the hydroxide, is so powerful at ripping away the hydrogen that it indeed will take off that hydrogen. Now, of course, if that's the case, it is converting it into the acetate ion that we have over here. And it just so happens that, if you recall from the group quiz that we're doing right now, a weak acid will have a strong conjugate base. Well, while this is a relatively strong conjugate base, it's the reason why the hydronium is so readily picked up by this acetate ion. It isn't nearly as strong. This base, I'm sorry, right here, isn't nearly as strong as this base right here. So the hydroxide essentially overpowers the weaker of the two bases here and forces the formation of the acetate ion. Okay? Now, obviously you can see here that in this case, I only have enough buffer solution to be able to consume, what do I have here? 1, 2, 3, 4, 5, 6. 6 of the hydroxides. Okay? And obviously there's a limited capacity. Now, you would never have just 6 of the acetic acids in a buffer solution. You would have millions upon millions of them. But that does mean that there is a limited capacity for a buffer to be able to absorb the hydroxide, or in this case, because you need the acetate ion and you have a limited number of acetate ions, a limited capacity for it to be able to pick up and sponge up all the hydronium. And we refer to that capacity as, no surprise here, buffer capacity. And simply put, buffer capacity is the amount of base or acid that a buffer can neutralize before it's overcome by the excess hydroxide and the hydronium. All right, so buffers are pretty cool things, and they rely on a lot of your understanding of the concepts of what a weak acid is, and in some way even Le Chatelier's, because when you add something to one side of a reaction, it's going to make it proceed to the opposite side. And I hope this is something that you understand.